Okay. Okay.
Maybe you can write larger.
Yes. I guess I should. You can read the title. Okay. Okay. So an introduction to the low levels of the continuous Weihrauch degrees.
Okay.
Good. Then yes. Yes, I can start. Okay. So as I was saying, difficult to say for me how. Yes. So I don't know why I didn't. So he just says recording, but it didn't say. Difficult for me to say how interesting this will be to the crowd here, considering that it's not too proof theoretic, but well, this is what I was doing is once when I visited last month, so you might as well get an update. And also try to give maybe somewhat different introduction as to why all these Weihrauch shenanigans were introduced in the first place. So let's try. So point one, the basics. And well, yes, I should tell you what I mean by the basics. So the fundamental object of all of these sort of field studies, so to speak, are represented spaces. So a represented space is just either pair x delta x, where x is a set, and delta x, I should write it like this, is a map from a subset of their space to x, if I call it partial transaction. So this is so to speak, a convoluted way of saying that we are working with quotients of subsets of their space. And namely, what you should keep in mind is the following. So we're trying to do topology in a certain time way in spaces more general than their space. And we will see, so we see X as endowed with, I think it's called the finite topology. Used by delta X. So the topology is in a certain sense automatic. It is the finest, so on average, it's the finest topology that makes this map continuous. Okay. Okay. And so this is one of the fundamental objects. And well, the idea of why you want this definition is sort of clear, right? So if you want to do, maybe not for topology, but for computability, let's say this is the obvious, in a certain sense, attempt that you do if you want to do computability in spaces more general than their space of the natural numbers or things like that. Okay. So and then partial multifunction. Between represented spaces x delta x, like that. Partial multifunction f, but no, okay. Between represented spaces x and y, just
what is the domain of delta x open?
The domain of that x could be anything, okay, which is part of where the generality comes in and the sort of problems. Yeah, I mean, it's a good question. The domain can be anything. Is a relation. So okay, so partial multifunction is just a relation. Is a relation, say f subset of x and y. So as we will see, so that's the reason why I use a different term, but we see them as functions. So yeah, quote unquote functions in the sense that when I write domain of F, it is clear what I mean. So these are the points of X such that there exists a Y, such that X and Y belongs to F, and same thing for so the domain of X are points X of X such that there exists a Y in Y, such that yes, that's right. X, Y belongs to F. And for every point F of X is equal to the set of Y's, I mean, the obvious thing. So up to now, this is just a very sort of not even particularly original way of looking at relations. So, a realizer for a partial multifunction F. Let's say F from X to Y, right? So here this is for short, I write them like this, right? So a partial multifunction from represented space X to represented space Y. I mean, I can simply write it as essentially a function such that the domain is a subset of X. Also here, there's something, I mean, I will not be too precise with the notation, right? So technically speaking, I'm identifying a set with the represented spaces, let's say, having X as first component. This is not well defined, right? So we will see examples of sets which admit multiple representations, and then I should use different terms. So technically, so we should say something like X bottom, I mean, underline X is equal to this guy, and so you should write something like this. But never mind. I will not do it in the sense that it should be clear from context what is going on. Okay, a realizer for this partial multifunction is a function F from a subset of Baire space to Baire space, such that before writing the definition, it's quite clear what should happen, right? So so that this diagram commutes. Although they're not very precise. What does it mean that it commutes? So by it commutes, I mean that for every X for every P in the domain of F, in the domain of delta, sorry, I first do delta, of F composed delta X, we want that, well, delta X F, so this guy is here. Delta Y F of P belongs to this set here. Right, so we cannot speak of equality because technically we're just working with sets. So this map maps points to sets, but I surely can ask for it to be contained, right? So I'm simply saying, so this guy is a generalized.
That's subset.
No. So this map, right? You first apply F, then you apply dy, and this maps points to points. So you are given a point of Y as a result. And what you ask of this point of Y that you're producing this way is that it belongs to this set. So it is a bit convoluted. I mean, I reckon it is a bit convoluted, but let's say the intuitive idea that one should have is just that this, I mean, this diagram commutes in the only way that you can make it commute.
Also very quickly, what is F is undefined?
Yes.
Everything we want.
Exactly.
So that's okay.
that's by intention. That's a very good point. So this will, that's I mean, not a major spoiler, but it is a spoiler in the sense that you just found the bottom degree in all of the structure that we want to define, right? So the function that is nowhere defined. Okay, so I didn't say how I want to compare them, but something that is realized by everything is clearly quite weak. So yes, this is by design. And now, okay, I think I try to squeeze the final definition, and we will say that a partial multifunction is continuous, respectively computable. If it has a continuous, respectively computable realizer. Okay, so I guess it's high time we give an example if you've never seen it. So there are, so I hope we will be able to see. So we should see some non-trivial examples, but at least for the start, I think a trivial example is better. So something stupid that comes from combinatorics. No, subset. First I define how I compare them. So we say that f partial multifunction from x to y. Okay. Continuously. Weihrauch reduces G WZ, and this will not be pleasant if there are continuous or computable functionals KH from their space to their space, such that this function, so the function that the function that to a point P in their space associates this function list of integers. So that for every realizer G of G, sorry, for the most important bit, of course, the map that could be associated K of X. This map here is a realizer of X. Okay, so this is a fairly complicated definition for something which is actually relatively simple, right? So I'm telling you sort of which sort of manipulations of the input and of the output are allowed, so respectively continuous and computable. And what I'm saying is that a multifunction is simpler than the other if provided you're allowed to fiddle a bit with the input. So you can modify the input, apply the function that you're trying to be stronger, and then somehow computably or continuously go, let's see, give me an output that should have been the output of the function. So now it's better to give an example. I mean, of course, this is so for instance, I think I've done it very times, but let f in the function that takes coloring of omega with many colors and outputs infinite homogeneous sets. So basically, this function is you can see it as the pigeonhole principle. And again, okay, here I'm cheating in the sense that I didn't give you a representation, but the representation of this space is obvious, right? So this space you can simply see as being directly a subset of bare space. And you say that this subset of bare space such that, well, these are the points of bare space that only takes finite element values. And well, this one you can see as a subset, like the output space, you can see as a subset of the Cantor space, which is itself trivial as subspace of Cantor space. So in this case, the representations are trivial. And G you can see as so infinite graph. G will be a Ramsey theorem, okay? So infinite undirected graphs. And they will be mapped to, yeah, how do you say? So infinite, again, infinite homogeneous set, I should call them. So infinite connected or totally disconnected subgraphs. Again, here I'm cheating in the sense that I'm not giving you the representation, but the representation can again, so it's sort of trivial. So the point is that here we don't care about the topology, right? So this is just an example of the computable setting. When the topology matters, we will see that we have to be careful with the representation. But in this case, you can just say, okay, infinite, let's say countable. So you can simply see this guy as being represented by Cantor space again, right? So you suppose that every number codes for a pair of natural numbers, and you assign to this pair, you assign 0 if there's an edge between them, and you assign 0 otherwise. So this is a perfectly fine representation. So let's say you always assume that sort of the underlying set of the graph are the natural numbers, and you simply tell me when there's an edge and where there isn't an edge. And here we can use the same sort of coding as before. So here it is just enough to code sets. So you just have to tell me which numbers I want to consider in this subgraph. Then what happens is obviously that F Weihrauch reduces to G. Why? Well, because the only, let's say, K will be trivial. So in many ways, this is not the best example. Why? Because, well, okay. So to every coloring, we associate a graph as follows. So suppose P is a coloring of the natural numbers into a certain number of colors, which is finite, let's say K, and say that then H of P is the graph on omega such that okay, there is an edge between N and M, if and only if P of N is equal to P of N. Something very trivial. So how do you produce it? So you're given your coloring and you want to computably produce an infinite graph. So you sort of go through you go through the pairs coded by elements of omega, and you decide whether to put an edge or not. And you can computably check whether to do it because, well, you know where to look in the coding of the graph. Okay, so this is your H. At this point, you don't even, so this is a so-called strong Weihrauch reduction. And this is the case because now, if you're given any realizer of Ramsey theorem, let's say, you have a function that to every graph associates an infinite subset, an infinite homogeneous subset. And then, well, of course, then you just have to go, back. So if it is an infinite subset, it cannot be totally disconnected because there are only finitely many colors, so it will be totally connected. If it is totally connected, by definition, it will be homogeneous. Stupid example, but it should give you an idea of what is going on. So this is a very complicated definition to tell you that, well, we are only witnessing uniform reductions, let's say. So you say that there's a uniform way of simulating a problem using something else. Again, the definition, let's say, it could be much simpler if you didn't have to consider these. I mean, so the function P K, G, H, P would be much nicer to write, but then this gives this, so this is too sensitive, right? You still want to have access to the original input. This is all that is going on. We will see examples of why this actually matters. Okay, so and how are computability and continuity related? Well, I mean, I assume you know, but it is easy to see. So a function h from a subset of omega of bare space to omega is continuous if and only if we can see it like this, if and only if it is a computable function with a certain oracle. Well, why is it the case? I mean, this is a relatively known fact, but since I will sort of need more than this, I guess we might as well see. And the point is that H, like this, is continuous if and only if there is a function H from finite strings of natural numbers to finite strings of natural numbers such that H of X, I think I've been, okay, I've been calling them P's for reasons, okay. H of P, so for every point of the bare space in the domain of H, this is equal to the limit for n goes to infinity of H of X restricted to n. I mean, this is not particularly surprising. I mean, after you see it written down, you say, oh, well, yes, of course. This is exactly what continuity means. It means that the H is just the result of a limit approximation of itself. But the point is that, well, the limit approximation, you can code it by a real. This code is the oracle that you need in order to carry out the computation. I mean, nothing particularly surprising here, I guess. So, so in particular, what does it mean? So it means that we can always see these functions here as basically Turing functionals. The point is that in the continuous case, we also allow them to have access to an oracle, a fixed oracle, but an oracle nevertheless. But in a certain sense, the underlying procedure should remain the same. So they always, I mean, in both cases, they code a certain computation. Whether this can access some external data or not is what determines whether you're in the continuous or in the computable case. Okay. Okay. So something. Why do people care? Why do people start caring about Weihrauch degrees and all of this framework in general? Well, this framework can, to say it vaguely, can be used to do topology, let's say, abstractly in a certain sense. So for instance, right, the first observation is that if so I'll do this and then I'll explain. So give me two functions, two partially multivariate function, one from X to Y and G from Y to Z. We define the composition of them. So decomposed with F is given by the partial multivariate function from X to Z, such that the domain of G composed with F is equal to all the X in X, such that f of x is a subset of the domain of G. And then, G of f of x is equal to the z's in Z, such that there exists a y, such that Z belongs to gy and y belongs to f of x. Now, why am I spelling this out? Because this definition of composition is different from the composition that you usually put on relation. And this is the main reason why I bother calling them partial multifunctions at all. So by this, we can say that, let's say, the cut, so represented spaces with continuous or computable multifunctions and composition defined this way form a category. So it is a bit convoluted, but the reason why it is generally accepted that you call them differently than just relations is because, well, if you recognize that they compose in this way instead of just the composition of relations, then they give rise to, let's say, a nice structure. Moreover, if instead you restrict your attention to represented space with continuous or computable functions, then this category is Cartesian closed. And this is what you care about. I mean, to an extent, these are all trivialities, but this is why this whole business started. So we should say something about it. If I'm able to. So as I was saying, if we consider represented spaces with continuous or computable functions as morphism, this category is Cartesian closed, in the sense that, this is basically what I was saying here in a certain sense. So the space of the continuous function between x and y is represented by, I should say, H before. Okay, so I'm being maybe a bit too quick now, but what I'm trying to say is the following. So I'm claiming that the space of continuous function between x and y, and again, so remember, between x and y is a represented space. Now, there are several things to pay attention to, in the sense that continuous function between x and y continuous in the sense of represented space. So I mean functions that have a continuous realizer. These may not, in this general framework that we have, correspond to continuous function between x and y. This is only true if the representation. So this becomes true if the representation is particularly nice. It is called admissible. In this case, everything collapses, but there's no reason to go into that. Just remember that just by looking at the definition, I'm only speaking for now of functions that have continuous realizers. Okay, how do we represent a function like that? Well, we give it the code of the continuous realizer that they claim to exist. Of course, so in general, if we were to look at the category of multifunctions, there are too many objects there. So there will be too many objects with the same name, and this is not something that we allow. So this is the reason why we restrict to functions, but never mind. So still, in order to do topology, this is essentially what you care about. So you're given a represented space, and in a certain sense, computably, you can, let's say, if you were in the computable setting, you would have a computable way of moving from spaces to well, the functions between them, and define the function eval computably and everything else like that. In the continuous case, the function eval will be continuous, and so on and so forth. So you stay there. Okay. So now, for instance, functions. Are represented by a code of the realizer. Okay. Then, for instance, okay, consider the space, so the Sierpinski space. So one way of how you can use all of this framework, and say whether it is interesting or not, is consider this represented space. You have 2 points, top and bottom, and the representation is given by, well, delta S of the constantly 0 point is equal to bottom, and delta S of everything else is top. Well, then what topology do we have on the Sierpinski space? The usual topology that we give on the Sierpinski space. So the open sets in this space are well, empty set, everything, and top, and the only closed set is bottom. Then we can consider this space, okay. Okay, so if you take for every represented space X, we can consider O of X to be the space of functions E from X to Sierpinski space, continuous functions. Now, my claim is that these this represented space is the space of open subsets of X. Or rather, what should I say? Sorry. What should I say? The following. So we can see, so as we were saying, these we can just see them as codes, so points of vector space. So I'm naming the open subsets of X by the continuous map that so if U is open in X, then there is Q of U such that Q of U of X is equal to top if and only if X belongs to U. Right? You can surely define something like this. Hence, we can see O of X as a representation of open sets of X given by delta O of X. So in this framework, we moved from a representation of a space to a representation of the open sets of that space, for instance. But we can do more. So we could also find names of the closed sets of X with exactly the same representation. So a point of these, let's say the set that we want to represent are the closed subsets of X, but the name that we gave to them is a code for the complement. So in a certain sense, we use I sort of use notation and use the same. So again, you should sort of see what it means in this case, what I mean by doing topology without more abstractly. So it is an instance of so there is a framework developed by Escardo about which I should know more than I do, which is called synthetic topology, and this is an instantiation of that in a certain sense. So it is a category theoretic approach to topology in a certain sense. So for instance, in this case, you can say that a space X is compact if and only if the map is full from the open sets of X, the Sierpinski space such that is full of, let's say, P is equal to true if and only if, let's say, P is equal to X, is continuous. So you can characterize compactness of a space instead of speaking. I mean, of course, the definition will be equivalent in the end, provided X is a representative space. Instead of saying that, instead of giving the usual definition by saying that well, a space is compact if and only if any open covering of it admits a finite subcover, you can phrase it in terms of maps. So you say, so you can say that X is compact if and only if this map defined this way is continuous. And okay, so this is in a certain sense a triviality, but it sort of you can see that it allows you to move to sort of computable topology in a certain sense. So if everywhere here I were to remove, so I were to speak of computable maps instead of continuous maps, then I would have a possible definition of what it means to be compact in an effective sense. So in this case, it means that you can actually compute this finite covering that you claim to exist in a certain sense. And this is where the power of this setting comes. Although, I mean, to an extent, we are just renaming things that we already know. But well. Okay. Another example. Consider any A subset of X. Then the map that sends U to the set of no. Any representative space, sorry, the map that sends a subset of X, sorry, to the set of U's open sets such that the intersection of U and A is different from 0, is different from empty, is continuous. I mean, it's not particularly difficult to see, but it is an exercise. So now you start with any set and you map it to the set of open sets that intersect it non-trivially. Okay, when is it? Notice that. Let's say, let's call this map, I don't know, V. And we notice that V of A is equal to V of B. If and only if what? If and only if they have the same closure. right? Okay, I mean, if I set U intersect A, then it will also intersect its closure. If it misses it, it will also miss the closure. Let's say this map is well defined, provided that we define just closed set. So see this map. Meaning another representation of the closed sets of X, right? So if I take a closed subset of X, this time the name that associates to it is the name of the open sets that intersect it. So in this case, is called U of X, so the set of the overt, so to speak. And this is an example of what I was saying before. So now I came up with two represented spaces, which are different because the representation function is different, but the points that they're naming, so to speak, are the same. So in this case, I speak of closed sets with negative information. So I'm telling you what the complement looks like, and the complement is represented in a certain tame way, in the sense that the complement is just an enumeration of the complement, so to speak. Whereas here I'm giving you the closed set with positive information. So I'm telling you all of the open sets that do intersect that closed set that you're referring to there. And well, now, a problem that you may want to, in general, problems on these spaces that you want to study are choice problems. So, choice problems are interesting, and one choice problem that comes up from this framework is the following. So suppose it's called overt choice over X. So VC of X. So suppose let's say the domain are non-empty closed subsets represented as in V of X. So I should say that the domain is V of X, but not all of it, just the closed subsets of X that are not empty. And what you want to output is a point in that set. Right? So what you can ask is, so you give me, so you know that you have a closed set. It is described in a slightly non-standard way, in the sense that what you're telling me about that set is the list of open sets that intersect it. How difficult is it to produce a point in it? Well, okay. So for instance, it is a theorem by the Brecht. Pauli Schroeder, that if X is a co-Polish space, so something that we define. Exactly one of the following happens. So one, X is just a good Polish space. And DC of X and the over choice problem associated to X is continuous. So it is as simple as possible, let's say, without being an over-defined, or what? X does not have a countable base of open sets, but it is okay. Unison. So closed sets are determined by convergence of sequences, let's say, and the over choice for this problem has various degrees comprised between two very known characters, and we should see more about this guy in a while. Or X is not even Fresnel Wilson. And VC of X is stronger when it computes LPO. Right. So when I put a star, I mean continuous variable visibility. So in this case, let's see, looking at how these sort of choice problems related to a certain space, so let's, in a certain sense, looking at how strong they are tells you an awful lot about the topology. So what is a, okay, so copoly spaces are a generalization of Polish space. A copoly space is just a direct limit. Let's say you can consider it as a union of compact Polish spaces. So in particular, every Polish space is copolish, but an example of a co-Polish space, which is not Polish, is, for instance, the set of polynomials over the reals, depending on the polynomial. So you know that as long as you, let's say, the over choice problem is trivial, then your space is actually Polish. If it has, in a certain sense, bounded complexity, okay, then your space does not look spectacularly nice, but it's still not terrible. If it computes a certain other function, then your space is actually terrible to look at. So, and there are a bunch of these studies. So I guess this actually tells you more about why people care about all of these, or why they care at the start about all of these framework or reducibility and variable reducibility, and what it actually has to tell you about something that is more general than just combinatorics. Okay, but well, in particular, we will care about this guy here. So ACCN. Okay, actually, so it's a LPO. I guess it should be relatively known. So it's a limited principle of omniscience. It is essentially the problem that, given a sequence, it tells you whether it is constantly zero or not. Whereas ACCN, this surely is not particularly known, and it's a problem that looks stupid, but it actually isn't. So it gives it's the problem that takes as instances sets, closed sets of X. Sorry, closed sets of, well, let's say the natural numbers that are either the natural numbers itself or n-1 point, and we see this as a subspace of A of X. So the way we name these closed sets is given by this representation. So we just have an enumeration of the complement. and what it outputs is well, a point. It's a choice problem, right? So a point. A point in the closed set that you selected. So it is a very very weak choice problem. So you have a closed set. Of this closed set, you know that it is either trivial, so it is either everything or almost trivial. So just one point is removed. And of this guy, you want to remove the point. Well, so this guy shows up a lot in these sort of considerations here. So whenever you want to bound, so it appears naturally as a bound to many such functions, let's say. And yes, it should play a role in the following if I have any time to speak about it. This was meant to be bigger that. Okay, so I guess what I should say is that these degrees here, they count as relatively low degrees in the Weihrauch lattice. So in this, I mean, these and several related questions make the sort of degrees closer to the identity in the Weihrauch lattice an interesting sort of hunting ground, so to speak. So the general question that was asked by, again, Schroeder some time ago is, well, how do the low continuous Weihrauch degrees look like? Well, part of it was, I guess, already answered by Philip. So we know that there's a bottom degree. So the nowhere defined function surely is computed by everything else. In the continuous Weihrauch degrees, then we have the degree of the identity. And well, in every continuous function has this degree. Like this was the reason, I know I erased it, but this was the reason why I kept so why we had the sort of input function. Okay, so what we were saying was that this a function so when I was saying when a function f reduces to a function g, the definition of the reduction was that if G is if big G is a realizer of small g, then this guy is a realizer of the function f. Well, why does every continuous function reduce to the identity? Because if a function is continuous, then I can forget about this part and simply simulate that function using this k. Right? This is a perfect example of why we want to have this p here and not just care about continuous variable and not strong variable reducibility, right? So all of the continuous functions fall in this degree. But then what? So is there two? So is there another degree above it, namely is there a smallest discontinuous Weihrauch degree? Well, and the answer is it depends. So the answer is no if you assume axiom of choice, yes if you assume axiom of determinants. So I will not tell you about the no, because I mean, it's just a construction that needs something very weird. But it is interesting to see about the, I mean, how the yes, yes, how the axiom of determinacy helps you saying yes. Okay, and well, the idea is due to Bratka. Definition, we say that f x to y is effectively discontinuous if there is a function d there is a continuous function d from omega to omega that's for every q in omega to omega. Two things happen. D of q belongs to the domain of f. Well, okay. Because we're still working in the representative spaces. And dy of d of q of d of q does not belong well, to f of ux of q. But you can see where the name comes from, right? So I'm saying that something is effectively discontinuous if you have a continuous function d that tells you why, essentially, why the candidate for a realizer number q, let's say, candidate of continuous realizer number q, or coded by q anyway, is actually not a realizer. So I'm asking you to move, I mean, of having a continuous way of moving from let's say, index for a potential realizer to witness of non-realizability. And well, the point is the following. And where determinacy comes into place is when it comes to produce such a thing. Okay. And to do this, we define the wage gain for function f from, in this case, let's just look at bare space to bare space. So suppose that we have a partial multifunction from bare space to bare space, then the wage gain for this function is a two-player game. Played like as follows. So player one plays a certain string x0, player two responds with a certain string y0, and so on and so forth ad infinitum, where xi, yi belong to just a string from omega. Then two wins if actually I should say okay. So and let's call x is just equal to x0 concatenated with x1 concatenated with etc. Y is y0 concatenated with y1 etc. And we say that two wins if x does not belong to the domain of f, which is also the case if, for instance, at a certain point, y instead of playing, he keeps playing the empty set. If he keeps playing the empty set, he only produces a final string. This is clearly not an instant, I mean, not a point of the space. Or if x, y belongs to f. So in a certain sense, this is a stupid game, and one wins otherwise. So 2 wins if either one fails to produce a point, or if whenever one succeeds in producing a point, then player 2 succeeds in producing an image of this point. And one wins wins otherwise. And the point is what? The point is, okay, here I put on something. Here. Where F is continuous. Okay, so this is a theorem that ZF plus, I think, dependent choice. F is continuous if and only if 2 has a winning strategy. And this is actually quite easy to see, right? So, because what does it mean that 2 has a winning strategy? 2 having a winning strategy basically is the age that I was telling you about before. It means that provided you have some a finite amount of information about the point that is being produced by player 1, where that finite information is enough to sort of give you a neighborhood of where your point should land in, I mean, where the point of the image should be. And this is easy. What is not too easy to see and requires some thought is that F is effectively discontinuous if and only if 1 has a winning strategy. Well, one direction is actually quite easy, right? So if 1 has a winning strategy, you can see how this gives rise to this function here. Essentially, because, well, you say, okay, suppose the player 2 is playing according to continuous function of code Q, and you use your strategy to produce a point like this. And by the fact that strategies are defined on strings, this function will be continuous. So in particular, answer under determinacy, every function, every partial multifunction, every multifunction is either continuous or effectively discontinuous. And the point of effectively discontinuous functions is that you can come up with the simplest effectively discontinuous functions. Now consider this is the problem. It goes from full space to full space such that it maps a point of X is mapped to all the Y's inverse space with okay, right like this. Where U is any universal function, like your favorite universal function. So this is a very weird function in the sense that every point, like the image of every point, is everything except one point. And which one is that point? It's the point that would make the universal function correct on that one. So it is easy to see that these, okay, immediate that this is discontinuous. It is not that easy to show that it is effectively discontinuous, but you can do that without determinacy. The point is that it is on. So as long as we have determinacy, the fact that it is discontinuous, which again is obvious because any continuous realizer you have automatically diagonalize against, it also means that it is effectively discontinuous according to this theorem. And then something else that you can prove in ZF plus dependent choice, maybe even less, is that moreover F particularly discontinuous implies that it computes this. So this is your minimal degree. Okay. But it is of course annoying that it depends on AD for existence. Okay. So what we did, okay, I have to skip an awful lot, was to look at what happens in simpler cases. Okay, so 3. Namely discontinuous partial multifunction. And well, something that you can look at, and that, okay, it's actually particularly difficult. If F, again, let's just restrict to Verse space for simplicity, is a partial multifunction whose codomain is omega, then the wedge game for F is determined. And well, I mean, this is not particularly surprising, I guess, but it boils down to the fact that player 2 only has one non-trivial move. So I guess there are essentially 2 cases, but I don't know if there is any point in proving this, but I guess there are 2 cases. So suppose that there is an X in the domain of F such that for every n and I natural numbers there is an m larger than n and y extending x restricted to m and in the domain of F such that y does not belong to F of y, then one has a winning strategy. Right, you just have to spell it out essentially what it means for one to have a winning strategy. So I'm saying, well, so there is a particular nice case that we want to consider. So if there is an X such that as long as I keep enumerating this X, sort of I'm given infinitely many chances of avoiding any move that player 2 can make, then of course player 1 wins. Because player 1 only has to play around that point. And so either player 2 does not move, in which case he loses because it doesn't produce a point. Or if he does, well, I can prove him wrong. Okay, so in this case it's easy, and so the only thing that we have to prove is that well, if no such X exists, well, this is enough information build a continuous realizer of F. But if F is a continuous realizer, it means that it is continuous, and then we can use what we proved before and say that the 2 has a winning strategy. So in this particular case, there is no need for determinacy, and I guess so. It looks stupid, but it still is interesting in the sense that it means that when you look at first order parts of principles, so certain particular cone below every problem, then that cone, the structure of that cone does not depend on set theoretic assumptions. Okay, which is good news to an extent. Okay, so I guess the gist is that we can try to analyze the structure of that guy. So the structure of these sort of problems in ZFC. Well, so we just have to find the. Okay, so this tells us that we can sort of not use any set theoretic assumptions. And the next thing that we noticed, so how much time I have now, that if F, let's see again for simplicity from their space, and is this continuous? Then F computes ACCM. So again, yes. So if we are in the case in which, let's say, player one has a winning strategy for this sort of games, then this is enough to conclude that again, the degree about which I was speaking before shows up again. So it is also a bound for the strength. I mean, a lower bound for the strength of this sort of fund. And well, so is not particularly difficult. So you know, the player one has a winning strategy in the wage game. Game for F. Then what? We want to use this to this strategy to compute a reduction. So what we want to do, we want to say the following. So suppose that I don't know, S is in the domain of ACCN. Now, what is the ACCN? ACCN again was the almost trivial choice problem. So you know that you have a name of a closed set, which is either everything or everything minus a point. And how is this name given to you? It is given to you by an enumeration. So this sequence S is a sequence that either enumerates nothing. So for infinitely many steps of its existence, so let's get E, it's an enumeration. Either for infinitely many steps, it enumerates nothing, or after it enumerates a point, you know for a fact that it is done. Okay, and well, we just want to use as a winning strategy sigma in the wage game. So we want to use the strategy sigma as an oracle to compute this reduction. But computing this reduction, I mean, it should be easy. So it could be functional. Given, if you're given a map, if the function h does the following: h of e at step s, if e enumerated nothing, then each of the at this step is so the response of player one sigma to the fact that player two played nothing for infinitely many for as many turns. Otherwise, if E enumerates I at step S, playing sigma of empty set for S minus 1 many times, and then I. To play the response of the winning strategy to apply. So in this case in particular, we have well, say a strong reduction. So we don't need say the backward functional is just the identity, and we don't need to have access to the original input in order to produce this reduction. So if F is discontinuous in this sense, so if F is discontinuous and the domain, and the codomain is very tame, then we have a way of going back. What we noticed is that you can also, like, you have very similar behavior if the domain is stable. This. What we want to prove it is also the case that if f computes a function g from say, the completion of omega to omega to the omega is continuous, then this is also enough for f to be strong enough to compute ACCN. But if we just know of its behavior on the domain, the reduction is no longer strong. So in this case, we actually do need to have access to the oracle. So we can move a condition of tameness, let's say, from codomain to domain, but there is a price to pay. So it seems good. And well, the proof here is a bit more convoluted. But well, I'll just show to you that well, there is before I finish it. The sequential version of ACCN. Then we consider the following problem. So sequential ACCN takes has as inputs the completion of omega. So either a natural number or let's say an infinite sequence that never let's say that never converges, or actually I should say, let's put it like this. This set here, 0 to the n, 1, 0 to the omega for n in omega. And that's the point 0 to the omega. So in this case, I'm giving you essentially a representation of this space. And this is telling you, so in Cantor space, like this will be the name, actually, okay. It should be, I guess, something like this. Using zeros. So this point here will be the point giving the name to 0. This will be the point giving the name to 1, and so on and so forth. And this, like the constantly 0 point, is the point giving the name to omega. And this maps to what? Well, let's say if n is equal to AB, then all of the points that are possible answers are so the only point that you exclude is the first component of n whenever you see it as whenever you see n as a pair. Now, and you can see that sequential n is strongly Weihrauch reduced to ACCN. And well, and now this is a problem with the right domain. Okay, the proof is not particularly difficult, but there is a certain amount of detailing that you have to do. And well, so in the end, what we get is that for long dimension, we have that the following are equivalent. So the following are equivalent for, again, let's forget about represented spaces for functions like this. So 1 ACCN Weihrauch reduces to f. who F computes a discontinuous function G with simple codomain, and F computes a discontinuous G with simple domain. Okay, so now you could do something like this for more general cases, namely cases in which the Cantor-Bendixson rank of the domain and the codomain go on, and you have a similar behavior, but then things split. So it's a bit more, it becomes a bit more complicated. But you still have a minimal degree, which is basically given by disjunctions of a CCN. But in that case, it seems that currently we are still using some determinacy for this case. So it is simpler to look at simpler domains if you go up with the dimension. Surely out of time. Yeah, sorry for the mess.
When you're using system of determinacy, it's also recover.
Good point. Yes, yes.
And we go along with recover.
Good question. Yeah, I think it's open. So yes, that's something that Vasco Baratka asked. So he calls this principle of determinacy for this game Weihrauch determinacy, and it should be between. I mean, of course, it's between AD and. I mean, well, it's below AD as a strength, but it is unclear how much you need to make all of this work, or what repercussions it has. So, but yeah, so the only thing that you notice that it is incompatible with the axiom of choice. So it already is a non-trivial use, so to speak.
Because insensibly you have all these investigations on determinacy or way are they estimates of
No, the honest answer, I don't know. I should check again. I don't know whether any progress was made in this respect, or the question was simply thrown out.
There's also what's called L of R, constructed with sets or only sort of model where you could have determinacy somehow.
Yeah, that's true.
It's no choice. But maybe you can check this Yuan.
Yeah.
But for this, you have very special kinds of games.
Yes. So yeah, I mean, you can surely. Yeah, I mean, surely full determinacy is not needed. Nothing else. Well, I'd say surely, but well, it would be very surprising if that was the case. But I don't know if there is any upper bound or any lower bound in that respect. But yes, so one of the reasons why we wanted to pursue this sort of line of attack was to see if at any finite level already the determinacy shows up. And I mean, whenever you have something which is not omega, let's say, whenever you have even by Cantor-Bendixson, so Cantor-Bendixson rank might not be the best measure of absolutely nothing, but already if you look at space in general of Cantor-Bendixson rank 2, their behavior is quite weird, because essentially you can go back to the very weird spaces that I was mentioning before. So you have space that are not countably based, even if they're countable, and strange things go on. So we might simply just need to find the right angle to look at the problem and see where the determinacy actually comes in. But yes, that was one of the reasons why we started looking at these Steiner versions of this continuity. Thank you very much.